Hi class, welcome to lesson 34. In this review lesson, we will describe both bond and molecular polarity. By the end of this lesson, you should be able to determine how strongly an atom attracts electrons in a chemical bond, determine the degree of polarity of a bond using electronegativity difference, and determine the polarity of a molecule. A nonpolar covalent bond is a bond that results when two identical atoms equally share electrons. There is equal sharing because the electronegativity difference is 0. This is very common when an atom is bonded to itself, like in a diatomic element. Remember, you are responsible for knowing the 7 diatomic elements. Looking at the electron cloud structure of the molecule in blue, you can see that the electrons spend an equal amount of time around each of the bonded atoms. A polar covalent bond, on the other hand, results when two different atoms are bonded that have different electronegativity values. Here, the electronegativity difference is not 0, and the electrons will be held more closely by the atom with the greater electronegativity. This creates a dipole, the prefix di meaning 2, pole meaning areas of charge. So in the molecule such as hydrogen fluoride, fluorine has a much higher electronegativity than hydrogen. So the electron cloud shows that fluorine attracts the electrons more closely in the chemical bond, while the hydrogen has less of an attraction for the electrons, so it has a smaller electron cloud. You can see the electron clouds of the three major types of bonds. Nonpolar covalent bonds show an even distribution of charge as electrons are equally shared between identical elements. Polar covalent bonds always involve two nonmetals, but the charge is unevenly distributed and the electrons favor the more electronegative element. Ionic bonds are very polarized. They are so polarized they have two distinct ions, a positive cation and a negative anion. The more polar a substance is, the more ionic its character, meaning the higher melting point and boiling point it will have. Here is a nice chart to help you understand how electronegativity leads to the different types of bonds. Ionic bonds are formed between metals and nonmetals, while covalent bonds that have an electronegativity difference exactly equal to 0 will be nonpolar, and covalent bonds that have an electronegativity difference greater than 0 will be polar. Here you can see how we can use electronegativity values on reference table S to determine bond polarity. In a bond between sodium and sulfur, we have a metal and a nonmetal. When a metal and a nonmetal bond, we always create an ionic bond. In the carbon-carbon bond, we have two nonmetals. These two identical nonmetals have the same electronegativity, so the electronegativity difference is 0, resulting in a nonpolar covalent bond. In the oxygen and fluorine bond, we again have two nonmetals, but they have different electronegativity values. We always want to find the absolute difference in electronegativity. So the electronegativity difference is 0.6, creating a polar covalent bond. Notice that when we look up the electronegativity difference of sodium and sulfur, it is a very great difference. That will give the bond very polar characteristics like high boiling point and high melting point, even higher than those of the oxygen-fluorine bond, and especially higher than those of the carbon-carbon bond. Remember, the greater the electronegativity difference, the greater the ionic character. So carbon-carbon has 0 ionic character, while sodium and sulfur have the greatest ionic character. So by now you should be able to determine how strongly an atom of an element attracts electrons in a chemical bond and determine the degree of polarity of a bond based upon electronegativity differences of the bonded atoms. Now we're going to look at molecular polarity. Molecular polarity is the result of both bond polarity and the overall three-dimensional shape of a molecule. For molecular polarity, we are going to have to examine if the molecule is symmetric or non-symmetric. The VSEPR theory, or valence shell electron pair repulsion theory, states that negative electrons found in bonds will arrange themselves so that they can minimize their electrostatic repulsion. Remember, like charges repel. We can use VSEPR theory with an acronym SNAP. Symmetric molecules are nonpolar, and asymmetric molecules are polar. It is important that you use the rules for correctly drawing the Lewis dot structures of covalent compounds in order to correctly apply the VSEPR theory. Here you can see that dihydrogen monosulfide is drawn correctly, where the bonding hydrogens are found at right angles. This molecule lacks symmetry on the vertical and horizontal axis. Since it is asymmetric, this molecule is polar. Polar molecules are always going to contain at least one polar bond and be asymmetric. Polar molecules are asymmetric along the vertical axis and the horizontal axis. One shortcut you can use to determine if you have a polar molecule in reagents chemistry is examining the last subscript of the formula. So here we begin with HCl. The subscript on the Cl is 1. 1 is odd. Since 1 is odd, this will be an asymmetric polar molecule. You can also see that if you draw a line between the hydrogen and the chlorine, this lacks symmetry. Water is another polar molecule. If we use the subscript trick, we can see that there is no subscript on the oxygen, so the subscript is understood to be 1. An odd subscript will always be polar. You can see that water lacks a line of symmetry on the vertical axes as well as the horizontal. Remember, SNAP, asymmetric is always going to make a polar molecule. Nonpolar molecules could have polar or nonpolar bonds, but all nonpolar molecules are symmetric. When we look at a carbon molecule, we actually have a polar bond. The bond between carbon and oxygen is polar because carbon and oxygen are two different elements. Oxygen has a greater electronegativity than carbon. But when we examine the entire molecule, we can see that it is perfectly symmetric. When we apply the acronym SNAP, we can see that symmetric molecules are nonpolar. So why do we worry about determining whether a molecule is polar or nonpolar? The more polar a molecule is, the more ionic its character, meaning it will have distinct physical properties compared to nonpolar covalent molecules. Polar covalent molecules tend to dissolve in polar water. They have strong bonds with high melting points and boiling points. These strong intermolecular forces cause polar covalent bonds to typically be found in the liquid and solid states at STP. In contrast, nonpolar compounds do not dissolve in polar water. They have weaker bonds and weaker intermolecular forces, leading to low melting points and boiling points and gaseous substances at STP. This leads to an important rule of chemistry called like dissolves like, which means polar compounds dissolve in polar compounds. Nonpolar compounds dissolve in nonpolar compounds, but compounds of different polarity don't dissolve. For instance, I'm sure you know that oil and water don't mix. That is because they have different molecular polarities. In the first image, you can see how sugar, a polar molecule, is able to dissolve in water, another polar molecule. In the middle diagram, you can see carbon dioxide, which is nonpolar. It does not dissolve in water, which is polar. This explains why, when you leave the cap off of a carbonated beverage, it will go flat because nonpolar substances do not dissolve in polar substances. It is important to remember that ionic substances are extremely polarized, so ionic substances dissolve in polar water. Notice how the ionic substance sodium chloride has dissociated or broken up into its individual ions. Notice how the positive hydrogen molecules arrange itself to be closer to the negative anion or farther from the positive cation. The fact that ionic compounds dissolve and dissociate in water explains why ionic compounds conduct electricity in solutions, because they have free moving ions. That is different than polar compounds that dissolve in water, like sugar. Sugar gets completely surrounded by water, but it does not dissociate into charged particles, so it will not conduct electricity in water. Let's practice figuring out if molecules are polar or nonpolar. The first compound we see is the compound for calcium oxide. Looking at the Lewis dot structure, we can notice that calcium oxide is ionic. We know it's ionic because its Lewis dot structure is drawn with each ion separated with brackets and a charge outside due to the transfer of electrons. Ionic substances are very polarized, giving them high melting points and boiling points, allowing them to dissolve in water. Next, we have the diatomic element bromine. Bromine is perfectly symmetric. When we apply the acronym SNAP, we can see that bromine will be symmetric and nonpolar. The same is true for diatomic oxygen. Again, the covalent molecule is perfectly symmetric and nonpolar. Hydrogen bromide is also a covalent compound between two nonmetals, but it does not have symmetry. It is asymmetric and polar. NH3, also known as ammonia, is also asymmetric and polar. So by now you should be able to determine which element more strongly attracts electrons in a chemical bond, use electronegativity difference to determine the type of bond between two bonded atoms, and determine the polarity of a molecule using the VSEPR theory and the acronym SNAP. This concludes Lesson 34, Polar Bonds and Polar Molecules. Make sure you take good notes and bring them to class. That way you can revise them. Write down any questions you have and ask them in class. Again, we want to make sure you have the best, most useful notes possible. Complete your homework in Google Classroom and put your Regents Chemistry reference table and calculator back in your backpack so you are prepared for class. I'll see you soon.